This is the first lecture of the third week, and today we're going to cover least squares assumptions. Here's an outline of the lectures that we're going to cover this week. The first lecture will cover the least squares assumptions. The second lecture will cover binary regressor. The third one will cover omitted variable bias, and then the last lecture will cover the causality and regression analysis. So in order for OLS estimator to be the best linear unbiased estimator, we had to make some assumptions. And these assumptions are known as the least squares assumptions. So what are these assumptions? The first assumption is that expected value of u given x is equal to 0. The second one is that x and y are independently and identically distributed. The third one is that large outliers in x and y are rare. And then the fourth one is that the variance of ui, or the error term, is constant for all values of xi, and we call this homoscedasticity. And then the last assumption is that there is no series multicollinearity. And we don't talk about that in this lecture because this only applies for the multivariate or multiple regressions. Let's talk about the assumptions one by one. The first assumption is that the expected value of u given x is equal to 0. What does this mean? So let's think about the ideal randomized control experiment. Let's say there is a pharmaceutical company that's interested in whether the cancer drug is effective or not. The first thing that the drug company has to do is randomly assign people into treatment and control group. Once you have people randomly into treatment and control group, you need to give the actual cancer drug to the treatment group and give placebo to the control group. In our mathematical term, giving the drug to the treatment group is x. There is some sort of outcome that we're interested in. So the outcome y that a drug company may be interested in is the rate of people's recovery. Since the drug company has randomly assigned the patients into treatment and control group, other factors that could potentially impact the outcome are evenly distributed between treatment and control group. So what are some of these factors? So these factors are UI. So these could be age or the stage of cancer. So if someone is young, you may be healthier. Or if your stage of cancer is not as advanced, you're also you're more likely to recover. So when you assign people into treatment and control group randomly, these factors, UI, are evenly distributed between treatment and control group, and we can safely say that expected value of u given x is equal to 0. When we don't have a random assignment of control and treatment group, for instance, say in treatment group, you have all the young people who are healthy, and in the control group, we have all the older people who tend to be sicker. When you give a drug to the young people, the outcome, it'll actually overstate the outcome because young and healthy people tend to recover faster, and then by giving a drug, it may seem like the drug is the reason why they recovered faster. So in ideal case of trying to measure the effect of treatment, usually you need to have control and treatment group randomly assigned. However, in a lot of cases, we have observational data where we cannot just have a treatment and control group. So in these cases, we really need to think hard about what it means to have expected value of u given x equal to 0. Let's go back to our original policy question of looking at the effect of student-teacher ratio on students' test scores. So let's say a district wanted to hire an additional teacher so that the student-teacher ratio actually reduces or goes down. Would this actually increase the test scores? We cannot really say that in our case because there are other factors other than student-teacher ratio that could also impact the test score. So in our model, test score is y, or the dependent variable, and student-teacher ratio was x, independent variable. But there are these UIs, the factors that could influence the test score that we didn't include in the model. Some of these UIs could be the quality of teachers or resources. The problem is that these UI and STR are correlated. So for instance, districts with lower student-teacher ratio, so districts where they have fewer students per teacher, they're probably higher income districts too, which means that they also tend to have a better quality teachers, and maybe they also have better school resources such as computer labs or science labs. So these are the factors that could be increasing students' test score. And vice versa. So if the student-teacher ratio is really high, so there are a lot of students per teacher, those districts may have lower income and generally have less resources and lower quality of teachers. And that may be the reason why the test scores are lower. In other words, there is a correlation between the error term and STR. So that means that expected value of u given x is not equal to 0. What does this mean? It means that there are some omitted factors that we're not including in the model. And when this happens, our result will be biased. We call this omitted variable bias. So the second assumption is that the observations, or xi, yi, are independently and identically distributed. So this happens when observation is sampled by simple random sampling, which means that observations are selected from the same population. Then you can say the sample is identically distributed. And if the observations are selected at random, then you can say that it's independently distributed. So let me give you an example. Say you're interested in the average salary of working adults in the US. And you're interested in taking 100 samples. You took 50 samples from Ohio and another 50 samples from New York. We can guess that maybe the distribution of salary in Ohio is different from distribution in New York. Because in Ohio, most people have similar jobs, so maybe the salary distribution is pretty similar across people, versus maybe in New York, there's more diversity. So in New York, there are people who are not making that much in hourly jobs, working in fast food restaurants, and there are people who are millionaires and billionaires who are CEOs of a company. So you can safely assume that the distribution from Ohio and New York are different. So if you're taking a sample from Ohio and other samples from New York, you cannot say that these are identically distributed because you're taking samples from different population. The second criteria that you need to select sample at random. So imagine, for instance, you're taking a sample from only people working in Wall Street. So in this case, most of the observations would have very high salary. and these are not representative of the average salary of entire US. So in this case, the observations are not independently distributed because you're not taking a random sample. When you're taking a random sample, you take a sample from Arkansas and random cities instead of just taking a sample only in people who are working at Wall Street. The main place where you encounter non-IID sampling is when the data is recorded over time. Another example where assumption 2 can be violated is when you have time series data. Time series data is a data that is collected over time. So for instance, unemployment rates, stock prices, and interest rates are all considered time series data. For instance, when you have interest rate plotted against daily per each day, here we have, say, today the interest rate was 4%, tomorrow the interest rate was 4.5%, and then the next day the interest rate went down to 4.4%. All of these are more or less correlated with each other. You never have a case where today the interest rate was 4% and then the next day it was 1% and the day after it went up to 10%. So since interest rate tends to be more or less correlated with each other from day to day, this actually violates assumption 2 because they're not independent. The third assumption is that there is no unnecessary outliers. So outlier is an observation that is unusually small or large. There are several reasons why you may have an outlier. One of them could be that there was an error in recording the value. So for instance, the height was supposed to be measured in centimeter, and some of the heights were measured in meters, and that's why you have outliers. It's also possible that outliers is actually valid. So in the case of trying to measure the average salary in the US, maybe you happen to have one data point that is way large compared to others. Because say you included Bill Gates information in your data points, this would be an outlier. What you do in this case is that it's very subjective. So first thing you want to do when you have sample is that you want to plot the data in scatter plot to see if you have an outlier. And once you realize that there's an outlier, you want to figure out what's going on. If there was an error, if you believe that there was an error in coding the value, then you can either try to correct this error or just delete the entire observation. But if you think that the observation is valid, then you may want to just estimate the model, trying to understand how this outlier affects your model. The way you deal with outlier can be subjective, so there's no right way to deal with it. But one of the other way to deal with situations like having Bill Gates in your income data is to top code the data. So what do you mean by top coding? It means that anyone who has, say, over $250,000 per year salary, you just recode them to have $250,000 instead of just using their real salary. So you basically cap the largest value of salary and estimate the model afterwards. So that's another way to deal with an outlier. Here's an example where an outlier affects your model. Here you can see that there is an outlier that is really far away from all of the other data points, and that's how you can tell it's an outlier. Without this outlier, you would have had a flat regression line. But when you include the outlier, now your regression line changes to have a slope. So you can see how one outlier can actually affect your regression a lot. The last assumption, the assumption number 4, is that is the constant variance of the error terms. We call this homoscedasticity. This means that the residuals, or your error terms, have approximately equal spread around the regression line. So for instance, when you plot the data and you plot the regression line, you can see that all the errors or the data points are more or less evenly spread out around the regression line. So when the constant variance of error term is violated, we call this heteroskedasticity. So in this second graph, you can see the violation of constant variance of error term because the error term, the way it's spread out depends on the x variable. So if you're at x1, the error terms are more condensedly populated around the regression line, whereas if you're at, say, point x3, the error terms are actually spread out more across the regression line. So the issue here is that there are different standard error formula for whether you have homoscedasticity or heteroscedasticity. The problem is that most of the regression software, such as Excel or Stata, their default function is the homoscedasticity only standard errors. And the problem is that if you are using this default homoscedasticity error, when you actually have heteroscedasticity, then your error would be underestimated. When your error is underestimated, you're going to reject the null more often than you should. In other words, remember our formula where we calculate the test statistics, and in this calculation of test statistics, you divide beta hat minus beta by standard error of beta hat. Since we're underestimating the standard error of beta hat, this increases our test statistics, which means that we reject too often. When you reject too often, that means that we find the coefficient statistically significant more often than we should. So the bottom line is that you want to use the heteroscedasticity robust standard errors, because if you have the heteroscedasticity robust standard error, but you actually have homoscedastic error term, then that's fine. But the other way is not okay. So when in doubt, it's always good to just use the heteroscedasticity robust standard error. So how do you do this in Stata? It's very simple. You basically do your regression model, but you include comma and option robust. And this should give you a regression output with robust standard error, meaning the heteroscedasticity robust standard error. If you don't include this in the Stata command, then Stata would actually compute the homoscedasticity only standard errors. And hence, if you don't have homoscedasticity, then your error will be underestimated. So I suggest in most cases to use the robust option unless you have a strong belief that your error terms are constant or your variance of the error terms are constant.